All right, let's look at what happens when we put a rod and move it through a magnetic field. So I've got a magnetic field drawn going into the page. I have a rod of some length L, and I want to know what the positive and negative charges are going to do. So what I'm going to do is I'm going to apply an external force and move it. That's all there is to it. But I really can't see what goes on with the charges. Now let's take a look at it, and this time look at the charges. So here are the charges. I'll take it and I'll slide it across the magnetic field, and now I see something curious. The charges move, but I didn't move them. So what did move them? Well, anytime you move charges across a magnetic field, they'll feel a force. That's the magnetic component of Lorentz force. So if I look at it this time, I can see that there's my open right-hand rule. B field's going into the page, thumb is going the direction of the charges. So even though the charges are contained in the wire, they are moving from left to right. That's why my thumb goes from left to right. So now it makes sense. They're not curved because I'm constraining their motion by putting them in the wire. Okay, so now I've got separated charges. What next? Well, anytime you get separated charges, you get an electric field. So when I look at this, it's basically a battery, and I've got an electric field going from positive to negative through the surface of the wire. And I know it's through the surface because we know that electric fields don't exist inside of conductors, and this is a wire. So I've got an E field, and that's equal to the magnetic component of Lorentz force. So QE, F is equal to QE, remember that old equation? QE, the force due to the electrical field, is equal to QVB sine theta. So as it moves, I set up this electric field, but only as it moves because I have to have that velocity. So QE is equal to QVB because it's sine of 90 degrees. The Q's go away, so E, the electric field, is equal to the velocity times the B field. Okay, that's kind of helpful, but there's more that I can do with it. Because basically, this wire is acting like two plates separated by a distance. So I know that the electric potential is equal to ED when I separate these two plates. So let's just replace D with L since it's contained in the wire and not the actual plates themselves. So V is equal to EL, or the electric field is equal to the potential difference divided by the length of the wire itself. Now I can take this V, the potential difference divided by L, and put it in my equation up above. So I get V over L is equal to the velocity times the B field. So in other words, the potential difference that I set up in this wire when I move it across an electric field is equal to the length of the wire, proportional to the velocity that the wire is moving, and it's also proportional to the magnetic field. It's kind of neat. Set up a little battery by swinging a wire through a magnetic field.